Hi, this is Cross Dot and Nabla, and in today's video we're going to be covering section 11.8 in our Calculus 3 series, covering lengths of curves. So before we go on to 3 dimensions of determining the length of curves, I like to go back to how we analyze curves in 2 dimensions and their lengths, right? So what we had is some arbitrary curve, let's just say it's something like this, and we'll just call it y as a function of x. And if we wanted to measure the area under the curve, it's pretty straightforward. We have x equals a here, x equals b here, and it's just x equals a to x equals b of f of x dx. However, in this case, in this video especially, we're not going to be coming over the area under a curve, both in 2 dimensions or 3 dimensions, but rather we're going to be covering it over the length of a curve, right? So how long would a curve be, or a line, right? A line's pretty straightforward to measure. You can just go from one end to the other, subtract the difference, and that's your length. But for curves like this, it's going up and down, left and right. How do we solve that? How would we solve for that? Well, nice little trick that we used in Calculus 1 was doing this. So we have some dx and dy. These are kind of large dx's and dy's, but if you get smaller and smaller, like this, you get the idea. We're mapping on a hypotenuse, right? And the smaller and smaller we go, we can solve for that, right? And as we know from trigonometry, a squared plus b squared equals c squared. And we'll just call this L squared. And we want to solve for L, right? So we should take the square root of this, and we want all these little dx's and dy's, right? What we do is we say from x equals a to x equals b, we want all of these little dx's and dy's. And we sum up all these to get L, right? L is our arc length, the total length of the curve. However, we don't have it in its final form because you have to integrate a function with respect to a variable. In this case, our function is y in terms of x, right? So we have to divide by dx squared on the bottom. This is going back to a very classic AP Calculus or Calculus 2 derivation that we may have done before. This keeps everything constant, and let me just move everything over to make it more visually understandable for you guys. We're dividing everything by the square root of dx squared, but also multiplying it so it cancels. So it doesn't cancel out, but it basically balances out the equation, and we still go from x equals a to x equals b. This is still equal to L, and then we get 1 plus dy over dx squared dx as our integral. And this equals L, and that's the derivation that we use to solve for the arc length in 2 variables. In 3 variables, however, it's a little bit different, and in this video we're going to be going over the other types of not parametrization, but solving for the arc length of these curves, both in parametrics, polar, and rectangular. And rectangular just refers to Cartesian, so it's like your standard x, y, and z. And your arc length for vector functions, like r of t, which is similar to this one up here, is just this, right? And if you think about it, it makes sense because this is your Pythagorean theorem in 2 variables. We're doing the exact same thing, just dividing everything by dt instead. Instead of us dividing by dx squared here, we divide by dt squared, right? And in this case, it's also the same thing, because if we had some vector valued function in space, like we had some point here, and it was going here and here and here, there's going to be some little dx, some little dy, and some little dz. And you would have to make 2 right triangles to solve for the total arc length, or the total distance from the origin, right? And we went over that in one of our previous videos, talking about how to solve for the distance from the center. I think that was the video with the spear example, right? And that's a very useful thing for us to have in our toolbox, especially to solve these types of problems. example 1 is kind of a classic. It is proving that the circumference of a circle radius a is 2 pi a. This one's pretty straightforward. Feel free to pause the video if you want to try this on your own. Just go right into it. Just say that r of t is this, a cosine t, a sine t, not parentheses, but a bracket like that. And then t is an element from 0 to 2 pi. And then we go into our integration. Take the derivative of this. It's going to be r prime of t equal to negative a sine t, a cos t. You square both of these guys, and you get a squared plus b squared, because the sine squared cosine squared, but we'll just show that for explanatory value. dt, this goes away, this goes away, this goes to 1, which parentheses there. It's going to be it's going to be at evaluated from 0 to 2 pi. 2 pi a equals L. And we'll just say that L is our arc length, like they do in these above examples above. Example 2 is a little bit more tricky. It's not as straightforward as example 1. It's example 1 is like the classic example to use arc length to apply it to other problems. In this case, it's a hypocycloid given by r of t equals cosine t cubed, comma, sine t cubed, where t is from 0 to 2 pi. The funny thing is that, like, these shapes, you don't often have to memorize them. I think in Calc 2 you might have had a test on, or a couple of multiple choice questions on, is this not a cycloid, is this a cardioid, is this like a rose petal, lemniscate? Like, this Calculus 3 isn't necessarily much about memorizing. I mean, some of it is memorizing formulas, but more of it's like understanding why do these things work. And in this case, this is like a conceptual thing. These things work because of what we're doing, right? And yeah, so we'll solve for this. Feel free again to pause the video. Try this one on your own. Go right ahead. Okay, so r prime of t, just jump right into it. Chain rule, I see, so it's going to be 3 cosine squared t sine t with a negative at the end, comma, 3 sine squared t cosine t from 0 to 2 pi. What I'm going to do is I'm going to do 4 times 0 to pi over 2, because just by looking at this shape, these are all the same. So it's like, why even bother going from 0 to 2 pi when we can just save ourselves some time? Square everything out. dt. This is going to be negative 3 cosine squared t sine t squared. And this is going to get us kind of a nasty algebra that we have to work through, but part of the struggle is the algebra, so we're going to work through that ourselves. And then this, we get 9. I see we can factor out a cosine squared sine squared, so let's do that. 9 cosine squared sine squared t. And I see cosine squared t plus sine squared t. That goes away to 1. Let's bring back our integral. Let's just say this is L, so it's easier for us to remember. L equals 4 times 0 to pi over 2 over 9 cosine squared t sine squared t dt. This is going to become 3 cosine t sine t. It's the magnitude, actually, so let's be conscious of that. But in this case, since we converted it from 0 to pi over 2, we don't actually have to worry about it, because it's always going to be a positive value for cosine t and sine t, right? Because remember, our unit circle, so we can just say that's going to be 3 cosine t sine t dt. Let's bring this elsewhere. let's bring this actually over to the other side right here. 0 to power 2, 4. And then we can use our little bit of a trigonometric, actually not trigonometric substitution, but it's going to be a trig rule that we can apply, where we know that cosine t sine t equals 1/2 sine 2t. And then we can just do this. We can say that's going to be 6 sine of 2t, because we divided by the 2 on the outside, and I pulled out the 3 in from the front. Save myself some time. And then this is the antiderivative, of course. It's going to be 1/2 cosine 2t, 0 to pi over 2. This is going to get us, multiply this by 6, of course, but we'll do that at the end. This is going to get us negative 1/2, right? Negative 1/2 cosine of pi minus negative 1/2 cosine of 0. So this is going to be cosine of pi is -1, so it's going to be 1/2 minus 1/2. It's going to be 1 times 6. So our answer is going to be 6, which is kind of funny because you look at a shape like this, you wouldn't imagine it be a whole number. You'd think it'd be some constant times pi, but in fact, it does give you 6 as a final answer. So yeah, pretty cool. Now we're getting into the 3D applications of this, right? So example 3 says that an eagle rises at a rate of 100 vertical feet per minute on a helical path, helical, I'm not sure, given by r of t equals 250 cosine t, 250 sine t, 100 t, where r is measured in feet and t is measured in minutes. How far does it travel in 10 minutes? So unfortunately, we can't just add up all the circles and all of this. We have to use the Pythagorean theorem rule that we learned earlier. And I guess you can kind of, this is not the best, not the highest quality example, but you can kind of see it a little bit where we're going a little bit out like this. There is a marked dx. There is some dy here, and there is a dz building up, right? And you can just say that, well, dx squared plus dy squared equals L, equals, I'll just say some p, some plane squared, right? You do p squared plus dz squared equals L squared, and then you can substitute that in, then solve for it, right? That's kind of the trick that we're going for. Now let's get to the actual differentiation and then integration. So feel free to pause the video again if you want to try this example on your own. And right here we have r of t equals this. Let's just do r prime of t to save ourselves some time. Negative 250 sine t, 250 cosine t, 100. And you integrate this from 0 to 10 because it's 10 minutes and t is per minute, right? Feet per minute. So at 10 minutes, it's going to reach to 1,000 feet in the air. The eagle will. And now we do our plug and chug. Save some time with the math. It's going to be 62,500 sine squared t plus 5,000 cosine squared t plus, 10,000. And then 62,500. Factor that out, you get sine squared t plus cosine squared t. That's just going to be 1. A lot of these examples with helixes and a lot of trig identities, they're going to come down to if you know your Pythagorean identities. So that's also really, really important. If you have a test or an exam, just remember those Pythagorean identities. Remember 2 sine t cosine t equals sine 2t. Remember your double angle identities. Remember your half angle identities. Those can come in very, very handy in problems like these. And this is just going to get you this. This is a little bit too long for my liking. Let's just make it a little bit shorter. Much better. And this just becomes 10 root this much, 10 root 72,500. We can factor this out. We can do 50. I see a 50 in there. 500. 500 times root 29, which is the same thing. When you get to this level of math, it doesn't matter as much about like the rationalizing the denominator or factoring out like perfect squares from your square roots. It's more about the application of, do you know how to apply like the formula from above, for example, right? Example 4 gives us Kepler's first law. This relates to like orbits around planets. So this is like a thing with physics, right? Planets don't revolve around each other in a perfectly circular format. It's actually elliptical. So from Earth's perspective, actually, if you look out from the Milky Way, we're not going in a perfect circle. We're going in an elliptical orbit modeled by like RT equals A cosine T, B sine T. We're not really concerned about the third dimension in this case because it's ultimately kind of irrelevant at that scale. And then obviously this when t is from 0 to 2 pi. And the thing is that the reason why there's no elementary solution for the circumference for an ellipse will show up in this example, actually. So we get to take our time with this. Feel free to pause the video if you want to try this one on your own. We can always just do this. Get your r prime t first. It's one of the most important things. We get negative a sine t, b cosine t, 0 to 2 pi, a negative a sine t plus b cosine t squared dt. And then we're going to get a squared sine squared t plus b squared cosine squared t dt. However, a and b aren't equal to each other. We can see right here where it said that if a is greater than b, then a is the length of the semi-major axis and b is the length of the semi-minor axis. So in this case, you cannot say that sine squared t plus cosine squared t equals 1 because a and b aren't equal to each other. If a and b were equal to each other, you would just plug that in first thing into the equation, then you can just solve for it. And in this case, this is how you would actually how you would actually solve for the arc length of an ellipse. The area of an ellipse is still going to be pi AB equals your area. That's not going to change. The arc length will. So that's a cool thing that you can learn. If you ever ask your teacher, why can't you do it? This is the reason why. For how to solve for the arc length of an ellipse. Arc lengths of polar curves. This is something like at the very end of Calc 2 you may have covered very briefly. It's the same idea, just like infinitesimal change in your theta and your r as a function of theta plus your dr d theta, right? And yeah, example 5, I will warn you, doesn't seem that intimidating, but it is kind of a beast to actually solve out and get everything done. So if you want the challenge of the trig functions, go right ahead, be my guest, but I would recommend using a calculator to solve for this answer. Some of these integrals will actually be in your textbook as like common elementary antiderivatives. And yeah, just try this one on your own. Go right ahead. It's arc length of a spiral. It doesn't seem that hard, but until you get to the actual integration, it does get kind of tricky. So yeah. All right, let's get into it. So r prime, we'll just say is 1. And then we get 0 to 2 pi equals theta squared plus 1 d theta. Now I think we all know where this is going. Either you can do one of two things. You can be a coward and you can use your calculator, or you can try your best and try your best to use trigonometric or hyperbolic substitution if you so choose to solve for the arc length of this beast of an equation, right? And I'm going to use trigonometric substitution because that's what I'm feeling today. All right, let's say that theta equals tan of x d theta equals secant squared of x dx. And then our trig identities are going to come in super handy now. Let's just say it's going to be, let's just say theta equals 2 pi, theta equals 0. I'm going to leave it as is for now. This is going to become secant squared x plus 1. Actually, no, sorry, not secant squared. It's going to be tan squared x plus 1 secant squared x dx. This becomes secant cubed x dx. And this involves some integration by parts that this one took me some time actually to solve for. So you're going to set secant squared x dx equal to your dv, your u equal to secant x, du equals secant x tan x, and then your v equals tan x. So it's going to be v du equals uv minus v du, and this is going to get very nasty very quickly. So it's going to be secant x tan x minus secant x tan squared x dx, and eventually what's going to happen for this is that you're going to have to use integration by parts again to solve this example right here. You're going to have to do I think you're going to have to do like secant x tan x dx. You have to do the derivative of tan x, u equals tan x, and it's a whole thing. But eventually, the result you will get to, because I'm cowering out early, actually, is this. Let's just use x to be consistent. So that part stays consistent, plus ln secant x plus tan x. And this result right here, actually, I can't get the parentheses, whatever. This result right here is actually the antiderivative for secant of x, which is kind of cool. You have to use some trig manipulation from either pre-calc or algebra 2, or whenever you learn polars, not polars, whenever you learn trig identities to manipulate this out, and it's like really weird. But ultimately, if you are just looking for the answer and you were one of those cowards that used the calculator, from this point right here, you should have gotten something like 22.256 as your final answer, which is pretty nice, pretty satisfying. You don't have to do all this disgusting, in my opinion, disgusting trig manipulation, integration by parts. Math is beautiful, but sometimes it gets kind of ugly. Example 6 goes on to the same idea. We're trying to solve for the arc length of the cardioid. This one's more manageable. I will say though, only thing that you should know is that 1 plus cosine 2 theta equals cosine squared, and 1 plus cosine theta equals cosine squared theta over 2. That will come in handy later on in this problem. And yeah, feel free to pause the video, try this on your own, and go right ahead. Okay, jump right into it. So it's me r prime equals, let's get into it, 0 to, let's say 0 to pi over 2, actually. Not 0 to pi over 2, 0 to pi. Let's actually map it on. So 0 starts at right here. I'm gonna go like this. Yeah, so pi would be perfect, because then we can just multiply by 2. It makes my life a lot easier, makes your guys' life easier at home, wherever you guys are watching. D theta, this becomes 1 plus cosine no, not cosine 2 theta. That'll come in later. 2 cosine theta plus cosine squared theta plus sine squared theta d theta. This becomes 2 plus 2 cosine theta. This goes to 1. And this will be taking in some very neat tricks that we took from earlier. You know, you remember your double angle, half angle identities. This is going to come in very, very handy. And this is still under the square root, 2 plus 2 cosine of theta, 0 to 2 pi, not 0 to 2 pi, excuse me. We said 0 to pi, make my life and your life easier. This will just become, this, but since it's going to be times that by 2, take the square root of this, it's going to be cosine of theta over 2, right? And if we have 2 plus 2 cosine of theta, like this is going to become 4 cosine, to me 2 cosine theta. And if you square it, it actually becomes 4 cosine squared theta over 2. Let me go right here. We can pull this right out. D theta. And this is going to become 2 cosine theta over 2. This is going to become 8 on the outside, because it's going to be 2 times 2, u equals theta over 2, 2 du equals d theta. I just did the u stuff in my head, makes my life easier. Keep on saying that throughout this video, man. It's going to be 8 sine of pi, not sine of pi over 2, it's going to be 8 sine of theta over 2 from 0 to pi. It's going to be 8 sine of pi over 2 minus 8 sine of 0. This is just going to be 8. This is going to be 0, so it's going to be 8 equals our arc length, which you wouldn't imagine this being the answer to this problem right here. And just to make sure, I'll plug it into Desmos to double check everything. Yep, it gave us 8. Perfect. And then one last thing we'll do is go over the arc length function. So we've been solving for the arc length, but now we're going to be using the arc length function. In these two examples, we're going to be converting from s to t, and s is just going to be our arc length function, where we have r of t describe a smooth curve for t is greater than a. The arc length is given by v of u, and remember when we say that v of u just refers to r prime, which we've been saying the whole time. This is actually one of the things we used in the first page. We kind of glossed over it, but this is the definition. It's the same thing as saying the magnitude of r, right? And this is going to help us solve for that right here, right? Give us right here too, actually. Perfect. Give us right here too. Perfect. This is going great. And we're going to try and parameterize this in terms of the arc length, right? So the arc length has to be 1 for it to correspond perfectly, right? And in this case, it does perfectly here, because if you take the derivative of this, negative sine t, cosine t, square both of those, you're going to get 1. But if you take the derivative of this, it's going to be negative 2 sine 2t, 2 cosine 2t. You square both of those, you get 2 is your thing, and then that's the correlation there. So whatever the arc length is for any function, in this case, this function that we're going to be doing, it's going to make sense for this. And let's just do it for cosine of 2t, right? So we got this. And we're going to say that this is s, right? Actually, let's just say that s is going to be, actually it has to be s, yes, it's going to be from t is equal to 0 to pi, so let's just say 0 to pi. And it's going to be 4 sine squared t plus cosine squared t. And that's going to be dt. So it's going to be 2 pi t equals L or S. And then we see that correlation there, right? So if the arc length was 2, that means that your S is going to be equal to 2t. But if your arc length is 1, if your magnitude of r prime is 1, then you get that, right? In this example 7 will make more sense. Find the arc length function s of t, and then find another description that uses the arc length parameter. So the arc length function for this is just going to be doing s of t equals this, 0 to t. And then we have to do the derivative of this. Plus 4 squared dt. We're going to get 4 sine squared t plus 4 cosine squared t plus 4 squared. This is going to be 4 plus 16, 0 to t dt. It's going to be 2 root 5 dt from 0 to t. It's going to be 2 root 5 t equals s of t. That's our arc length function. And if we want to use the arc length as a parameter, we can say that it's going to be s equals 2 root 5 of t. Because if this is 1, then we can say that the parametrization in terms of t is the same thing as it is in r, right? But in this case, it's not, because it's going to be 2 root 5 or root 20 in this case. So then we divide everything by 2 root 5 to get t by itself, and then we can plug it into the equation. We get r of t equal to 2 cosine of t over 2 root 5, 2 sine of t over 2 root 5, 4 times 2 root 5, or 8 root 5. And this should be in terms of t right here. Let me just fix that. And that is pretty much everything to know about curve in space and length of curves, how to solve for them, all the different equations, how to use the arc length function. And that's pretty much it. Thank you so much for watching. I hope you guys have a fantastic day.